You are welcome to the GMAT 41's Organic Chemistry class. In this video, we introduce aromatic compounds. You would recall from your basic organic chemistry, you may have encountered the word aromatic, where these compounds are cyclic and usually based on what? Benzene ring. Do you recall the calculus structure for benzene? Okay, you could see within it, at the point you have something like double bond, other points single bond. Alright, the fact that a compound has maybe unsaturated bond conjugated with saturated bond, let's say double bond conjugated with single bond, does it show that a compound is aromatic? The answer is no. Now the fact you have a compound where a single bond is conjugated, that is linked to the double bond, does not really mean that the compound is aromatic. There are criteria for aromaticity. For us to say that this compound is an aromatic compound, it must satisfy certain conditions. Now, what are the conditions therein? We have them on the board, okay, so we can just go through them. One of the criteria is that the compound must be cyclic in nature. It's not an open chain, it's a cyclic what? Ring. Then number two, the compound must be planar. So the carbon atoms in the ring must lie in the same plane. Number three, the compound must be completely conjugated. You see that, right? So you must have the compound in such a way that you have single bond linked to double bond. In hyperconjugation, electronic displacement of organic molecule, we encountered something like hyperconjugation, where we talk about electronic effect in organic molecule, right? You could hear something like tautomerism, electromeric effect, inductomeric effect, mesomeric resonance. We treated something referred to as what hyperconjugation, where you could see a single bond linked or conjugated, joined with a double bond. So such thing must be seen for an aromatic what? Compound. So the fourth one is that the compound must satisfy Huckel's rule. The Huckel's rule is a rule that helps us to determine or calculate the number of pi electrons in an aromatic compound or in a compound generally. Is that okay? That has pi electron. You know, once you have a double bond in a compound or a triple bond in a compound, then that compound must contain what? Pi electrons. That we studied under hybridization of organic molecules. These four criteria must be satisfied by a compound before you say that that compound is what? Aromatic. If any one of them is failed, then the compound is not an aromatic compound, even if it looks like one. We have these three examples on the board. We want to quickly use it to explain the concept of Huckel's 4n plus 2 pi electron rule. Now this is what we do. We use this formula to calculate the number of pi electrons, and then we do normal counting and compare. If the two electrons obtained in both cases, that is the one you obtain by counting and the one you obtain using Huckel's 4n plus 2 pi electron rule, if they are equal, then the compound is aromatic. But if they are not, then the compound is not aromatic. However, remember it must satisfy the first three conditions as well too, before you can talk about even the Huckels. Alright, now we have benzene here. Let's find out. It's cyclic already, okay? The compound is cyclic, it's planar. Now the number of rings, n, is 1, because n in that Huckel's formula is number of rings. So for benzene, it is 1. If you substitute it into the 4n plus 2 pi electron rule formula, you're going to get 6 pi electrons. Is that okay? Now let us count the number of electrons and see if it will be the same as 6. Let's go. How do you count? You locate the double bond, then you count up and down. Count the number of pi electrons up and down. So we'll come here. This is a double bond here. So 1, 2. There is no double bond here, so you come here. 3, 4. Then you come here, 5, 6. That's good. So by counting the number of pi electrons you have there is the same as the number of pi electrons obtained from what? Huckel's rule. Therefore, benzene is what? Aromatic. Is that okay? Now let us look at naphthalene, 2 linked or conjugated benzene ring. If you count, let's see the number of pi electrons you have. Here is double bonds. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then when you calculate using Huckel's 4n plus 2 pi electron rule, N is equal to 2. Substitute, you're going to get 10 pi electrons as well. So naphthalate is aromatic. What about cyclopent-1,3-diene? Is this an aromatic compound? Looking at it, it has a single bond conjugated with a double bond. You can see that this single bond here conjugated with this double, then this double conjugated with this single. But is this an aromatic compound? Let's find out. From Huckel's rule, the number of ring here is 1. So if you substitute n equal to 1 in the Huckel's rule there, you're going to get 6 pi electrons for this compound. Now let us count and see. Come over here where you have a double bond. 1, 2, then 3, and what? 4. So you see you have 4 pi electrons from 5 carbon atoms here by counting. Using Huckel's rule, you have 6 pi electrons. They are not equal. Therefore, this does not obey Huckel's rule. Hence, it is not an aromatic compound. In the next video, we are going to look at properties of aromatic compounds and then the IUPAC nomenclature of aromatic compounds. Let us now look at the properties of aromatic compounds. Okay, the first one is they are resistant to the usual addition reaction, which is generally characteristic of unsaturated compounds. Do you recall alkenes, right? Alkenes contains double bond, isn't it? We refer to them as unsaturated. So there are some reactions that they undergo. Something like decolorizing bromine water, decolorizing potassium permanganate. But you see, aromatic compounds, if you look at the structure, it shows a high degree of unsaturation because of the double bond that you see there, right? Does that not mean that they undergo similar reactions as alkanes? The answer is no. Is that okay? The answer is no. That's why this property says they do not decolorize bromine, they do not decolorize bromine water, they do not decolorize potassium permanganate. We want to bear this in mind. Is that okay? Hence, we cannot classify aromatic compounds. For example, benzene, we can't say it is an unsaturated compound. We can't say that. Alright, now let us look at the second property. They are comparatively very stable. They have low heat of hydrogenation and low heat of combustion. Is that okay? When you compare them to cycloalkanes, for example, cyclohexane, it's easier to hydrogenate cyclohexane as compared to hydrogenating benzene, which shows that aromatic compounds are relatively or comparatively more stable when you compare them to the likes of cyclohexane. Property number 3, they are planar and cyclic. We explained that already. Is that okay? All aromatic compounds are cyclic in nature and the carbon atoms, they lie in the same plane. Number 4, they obey Huckel's 4n plus 2 pi electron rules. We've already done that in the previous video where we calculated a number of electrons using this rule, and then we counted as well the number of pi electrons, then compared the both to know whether the compound is aromatic or not. All aromatic compounds obeys this Huckel's rule. Let us define resonance energy, also known as stabilization energy. It is simply the difference between the heat of hydrogenation calculated and the heat of hydrogenation obtained from experiment, or you can say obtained by observation. And this resonance energy, also known as stabilization energy, is what determines the measure of stability of benzene molecule. Let us now look at the IUPAC nomenclature of aromatic compound. We are starting with benzene, where we have one attachment, and cases where we have 2 attachments on the benzene ring. So we have these monosubstrate benzenes. The first one, bromine, is attached, so it has the name bromobenzene. Straight ahead. The second, we have methyl attached, so we call it methylbenzene. It's also known as toluene. The third, we have the OH group, that's hydroxyl attached, and we refer to it as hydroxyl benzene, also known as phenol. We have the benzoic acid, where the COOH group, that is the alkanoic acid functional group, is attached. So the name is benzoic acid. And then we have aminobenzene, also called aniline. That is where we have NH2, the amino group attached. What about nitrobenzene, where we have the NO2 attached? Then we have benzene sulfonic acid, SO3H is attached. Then we have acetophenone, where COCH3 is attached. Is that okay? Now, I want to state something, please, that in some cases, you see, like this one, methylbenzene, that's toluene, hydroxybenzene, phenol, benzoic acid, amino acid, nitrobenzene, benzene sulfonic acid. In some cases, we use them as the parent name. Maybe if you have another attachment somewhere on them, is that okay? We could take these as the parent name, while the other becomes what? An attachment. So, take note in case we meet a case like that and we choose to give the parent name in line with this, what you see here. Is that okay? Now, I want to look at that substrate benzene. Before we move on into that, where we have two attachments on the benzene ring, I want us to identify three positions called the auto, meta, and para position in benzene, depending on where the second attachment is cited from the first. Is that okay? And we use such designation when we have the same attachment or the same group attached to the benzene ring. Consider this. Imagine you have a group attached to this position number 1, and the same group is also seen on position number 2. So we refer to it as an auto position. What if in the situation you have a group in position number 1 and the same group is found in position number 3? We refer to it as meta position. Then finally you have a group in position number 1, the same group is found in position number 4. We refer to it as para position. Is that okay? Now let us see this. You can see that in the first position we have bromine. Then just after the next position you have what? Bromine as well too. This is actually 1,2-dibromobenzene, but we can still refer to it as O-dibromobenzene because the second attachment of this same group is located on the auto position away from the first. You can see the auto position is just the next position after the first one. The meta is the second position after the first. And then the para is the third position after where you cited the first attachment. Look at this here. Okay, when you have methyl attachments, two methyl attachments, is that okay, on benzene ring, we refer to it as xylene. Now look at this. On the first carbon atom here you have CH3, then on the third carbon atom you have CH3. The same group. So this is actually 1,3-dimethylbenzene, which you can still refer to as what? N-xylene or N-dimethylbenzene, because the second attachment is cited on the meta position. Then we have this, where you have methyl on the first. Then counting 3 carbon atoms away from that first, you still have methyl what? Attachment. So this is actually 1,4. This is 1,4. 1, 2, 3, 4. So 1,4 dimethylbenzene. Is that okay? 1,4 dimethylbenzene, which is still called p-xylene. Or you can refer to it as p-dimethylbenzene because the second attachment is cited on the fourth carbon atom away from the first one.